Okay, let's unpack this. Imagine yourself back in the late 19th century, physics felt incredibly powerful.
Oh, absolutely.
You had Maxwell's elegant equations unifying electricity and magnetism, predicting light was a wave. Newton's laws perfectly described how objects move, from planets to cannonballs. Thermodynamics explained heat, energy, how machines work.
Yeah.
It really seemed like humanity had, well, a complete, coherent picture of how the universe operated.
It was a stunningly successful era, really,
Hmm.
built on this bedrock of continuity and determinism. Everything felt smooth, predictable.
Right?
If you knew the starting conditions of a system, classical physics basically said you could calculate its future with, like, absolute certainty.
But as experiments got more precise, tiny cracks started appearing in that beautiful, seemingly finished structure. These weren't minor glitches, were they?
No, not at all. They were fundamental challenges that classical physics just couldn't answer.
And the story we're diving into today follows the linear progression of those challenges and how they led to, well, the most radical reshaping of our understanding of reality, the birth and development of quantum theory and technologies.
Exactly. We've been exploring a fascinating stack of source materials that trace this incredible journey. Our mission in this deep dive is to walk you through that timeline, pulling out the key discoveries, the brilliant, often reluctant minds behind them, and the mind-bending concepts that emerged.
Yeah.
Think of this as your shortcut to understanding the fundamental story of how physics went from a smooth, predictable machine to this strange, probabilistic realm, and how that transformation is now driving the technologies of the future.
So let's set the scene at the turn of the century. One of the biggest puzzles challenging physicists involves something seemingly simple:
Mhm.
how hot objects emit light. You heat a piece of metal, it glows, first red, then orange, yellow, white, even bluish at incredibly high temperatures.
Right, the everyday phenomena.
Yeah, but classical physics should have been able to explain the spectrum of that light, how much energy is emitted at each frequency or wavelength, but it couldn't, could it?
It really couldn't. This was known as the black body radiation problem. A black body is just this sort of ideal object that absorbs all incoming radiation and, when heated, emits radiation perfectly.
Okay.
The key was that the spectrum of this emitted light depended only on the object's temperature, not what it was made of. Physicists tried to apply those powerful classical tools you mentioned, Maxwell's electrodynamics and the laws of thermodynamics and statistical mechanics, to model the oscillators within the black body material that were thought to be emitting the light.
And what did classical physics predict? What was the outcome?
Disaster, essentially. Classical models worked okay for certain parts of the spectrum. Wien's law, for instance, described the shape well at high frequencies, but it failed at low frequencies. But when they tried to create a model that worked across all frequencies using pure classical reasoning, they hit what was later dubbed the ultraviolet catastrophe.
The ultraviolet catastrophe. That sounds pretty dramatic.
It really was. The classical theories predicted that the energy radiated by a black body would just increase infinitely as the frequency increased, especially heading up into the high-frequency ultraviolet end of the spectrum.
Infinitely.
Infinitely. This meant a heated object should radiate an infinite amount of energy, which is clearly absurd. Experiments show the energy peaked at a certain frequency and then dropped off at higher frequencies. Classical physics predicted the complete opposite.
Infinite energy. That's not just a little bit off. That's like a fundamental breakdown, isn't it?
It absolutely showed there was something deeply wrong with applying classical ideas about continuous energy distribution to this problem. The smooth, continuous picture just wasn't working.
Okay, and this is where Max Planck enters the story in 1900. Our sources really highlight his role as the reluctant revolutionary.
Yes, Planck was 42 years old, a theoretical physicist, very much part of the classical establishment, deeply committed to thermodynamics. He'd been working intensely on the black body problem, trying to find a theoretical basis for a formula he'd actually presented earlier that empirically fit all the experimental data, bridging the gap between Wien's law and other results that worked at low frequencies.
So he had the right answer, the mathematical fit, but not the why behind it.
Exactly. He was trying to derive his formula from the behavior of these hypothesized oscillators in the black body. And in what one source describes as a twisted chain of reasoning involving statistical methods, he found that to make the math work, he had to treat the energy of these oscillators in a profoundly non-classical way.
How non-classical? What did he have to do?
He had to make a mathematical assumption, basically, that the energy wasn't transferred continuously, but in discrete packets or chunks. The energy of each packet for an oscillator was directly proportional to its frequency.
Mm.
He introduced a new constant for this proportionality, the constant that now bears his name, h. So the energy of these packets was given by E equals hf, where f is the frequency of the oscillator.
E equals hf, this
Yeah.
tiny constant h, sort of a measure of fundamental chunkiness in the universe. But you said he was reluctant. He didn't just shout, "Eureka!"
Not at all. Extremely reluctant. Our sources really emphasize that Planck did not initially believe these energy elements, as he first called them, were a real physical property. He saw it as a mathematical workaround, a statistical trick needed to get the right formula.
Strict.
He didn't stress the discreteness because it seemed so incompatible with classical physics. He later described his introduction of H as an act of desperation. He felt his reasoning was twisted and confessed to experiencing ill success in reconciling this idea with the classical laws he held dear. He certainly didn't see it as the foundation of a new physics.
Wow.
He confined it mentally just to the black body problem, and definitely didn't use the word quanta with the later meaning of a fundamental energy packet.
So the very first step towards the quantum revolution was taken almost accidentally by a physicist trying to save classical physics from an experimental paradox, resorting to a mathematical trick he didn't fully believe in himself. That's quite a powerful lesson in how a scientific progress actually happens.
It really is. It often takes time for the true implications of a groundbreaking idea to be recognized even by the person who conceived it. And in this case, it took a young, sort of outsider perspective to truly see the radical potential.
That outsider was a 26-year-old patent clerk in Switzerland, wasn't he?
Albert Einstein. In 1905, Einstein published several remarkable papers, one of which tackled the same energy problem, but from a completely different angle. While classical physics viewed light itself as a continuous wave, Einstein, maybe drawing inspiration from the discrete nature of matter, atoms, wondered if discontinuity might apply to light as well.
Interesting angle.
He looked at the interactions of radiation and matter, particularly phenomena like black-body radiation, and showed, like others had found, that applying rigorous classical thermodynamics to light led to those same absurd infinite energy predictions.
So he confirmed just how deep the problem went.
Yes, but his insight went much further. He argued that elementary thermodynamics actually required light, in certain situations, to behave as though its energy were localized in discrete packets. He explicitly called these energy quanta.
Quanta, so he used the word.
He did. This was his radical interpretation. Planck's mathematical factors weren't just about the oscillators doing the emitting, they were a property of the light itself. Today, we refer to these energy quanta of the light as photons, and the energy relation is written EH lever F, or using the reduced Planck constant in angular frequency, E equals h bar omega.
Okay, so Einstein takes Planck's reluctant constant and says, no, this is real. Light is quantized. That's a huge leap.
Precisely. And he didn't stop there. He realized that if light is emitted and absorbed in these discrete packets, well, this should explain other phenomena too. His most famous application of this idea was to the photoelectric effect.
Right, that's where light hitting a metal knocks electrons off. What was the problem classically with that? Why couldn't the wave theory explain it?
Well, classical wave theory really struggled to explain some key features of the photoelectric effect. For instance, wave theory suggested that the energy of the ejected electrons should depend on the intensity or brightness of the light. A brighter light means a stronger wave, more energy transferred to the electron.
Makes sense, classically.
Right. But experiments showed the electron energy depended only on the frequency of the light, the color, not the intensity. Also, there was a threshold frequency. If the light's frequency was below a certain value, no electrons were emitted, no matter how intense the light was. And the emission of electrons was practically instantaneous, even at very low light intensities. A classical wave should take time to sort of build up enough energy to knock out an electron.
Okay, so the wave picture just didn't match the observations at all. How did Einstein's quantum idea fix this?
Beautifully. He proposed that light energy arrives in these discrete photons. A single photon interacts with a single electron, transferring its entire energy, hf, to the electron.
All or nothing.
Exactly. The electron needs a certain minimum energy, they call it the work function, to escape the metal. If the photon's energy, hf, is less than the work function, the electron can't escape, regardless of how many low-energy photons hit the surface. That explains the intensity independence below threshold.
Okay.
If hf is greater than the work function, the electron escapes with the excess energy as kinetic energy. This perfectly explained the frequency dependence, the threshold frequency, and the instantaneous emission, because the electron gets all the energy it needs from just one single interaction.
And this provided a testable hypothesis, something concrete.
Crucially, yes. Einstein's equation for the photoelectric effect related the electron energy to the light frequency and Planck's constant. It offered a completely independent way to measure H. And this made the idea really solid, something you could actually go out and test in the lab.
But it was still a battle, right? I mean, this particle-like view of light directly contradicted the overwhelming evidence for light's wave nature. Things like interference patterns, diffraction, only waves do that stuff.
Absolutely. It was incredibly controversial. Robert Millikan, a really meticulous experimentalist, spent over a decade conducting highly precise experiments to test Einstein's photoelectric equation. And while his results stunningly confirmed Einstein's equation and provided a precise value for H.
He confirmed the math.
Yes. But Millikan himself and many others were deeply skeptical of Einstein's underlying idea that light was actually composed of particles. They just couldn't reconcile it with interference phenomena. It's quite telling that when Einstein won the Nobel Prize years later, it was largely cited for his discovery of the law of the photoelectric effect, acknowledging the empirical correctness of the formula, but maybe not fully endorsing the radical photon concept right away.
So the wave-particle duality puzzle for light was just blown wide open. And Einstein himself kind of stoked that fire, didn't he? Showing that thermodynamics seemed to require both waves and quanta.
Yes, he truly sharpened the paradox. Light seemed to be both a wave and a particle, depending on the experiment or how you decided to look at it. While the idea of the photon became indispensable for explaining other things, like how X-rays scatter off electrons, it's the Compton effect, which earned Arthur Compton a Nobel Prize, the fundamental mystery of duality remained deeply unsettling.
Okay, so the idea of energy quantization, EHF, came out of black body radiation, got a huge boost from Einstein and the photoelectric effect. Where else did this strange quantum idea pop up next on our timeline? Did it spread?
Surprisingly, yes. As one source notes, some of the earliest and most widespread acceptance of quantum concepts actually came in areas that seemed pretty unrelated to light or radiation initially. A key example is the study of specific heats in solids, basically. How much energy you need to pump into a solid substance to raise its temperature by a certain amount.
And classical physics had trouble there too.
It did, particularly at low temperatures. Classical thermodynamics, using something called the equipartition theorem, predicted that the specific heat of a solid should pretty much stay constant as temperature decreases. But experiments clearly showed it dropped significantly, heading towards zero, near absolute zero temperature.
Another prediction failing to match reality.
Right. And Einstein, again, suspected quantum effects were the culprit. In 1907, he applied Planck's quantum idea in this totally new context. He modeled the solid as a collection of atoms vibrating around their equilibrium positions, like tiny oscillators. And he proposed that the energy of these vibrations, just like Planck's black-body oscillators, could only take on discrete values, quantized in chunks of HF.
So using EFF again, but this time for atomic vibrations inside a solid, not for light emission.
Exactly. And his simple model, even though it was pretty idealized, provided predictions for specific heat that matched the experimental data much, much better than classical theory, especially down at those low temperatures. This was a crucial step because it showed the concept of energy quantization using Planck's constant H wasn't just for light. It seemed to be a feature of energy and matter as well.
And who helped push this idea forward? Did it catch on?
The physical chemist Walther Nernst played a really vital role here. His own experimental work on specific heats further validated Einstein's quantum predictions. But maybe more importantly, Nernst was a real champion for these quantum ideas, actively promoting them and making sure they were discussed widely among physicists and chemists. Our source points out that he really helped put quantum theories on the agenda for widespread discussion,
making it impossible for the physics community to just ignore it. Which brings us to a landmark on the timeline, the first Solvay Congress in 1911. Sounds important.
It was a pivotal moment, described as the social debut of the quantum. It brought together many of the leading physicists of the era. You had Planck, Einstein, Poincaré, Marie Curie, Lorentz. Nernst himself was there. The central theme was literally radiation theory and quanta.
Wow, quite the guest list.
Absolutely.
Yeah.
And Einstein spoke there specifically on specific heats, further demonstrating the power and applicability of the quantum concept outside of just radiation. It was a forum where these strange, non-classical ideas were debated face-to-face among the absolute giants of the field.
A real turning point, then. where the quantum moved from being this fringe idea for isolated problems to a central topic of physics research. What other areas started sort of screaming for a quantum explanation around this time?
The structure of the atom itself, particularly the puzzle of atomic spectra, those discrete lines of light emitted or absorbed by different elements when you heat them up or zap them with electricity. You're probably familiar with how different elements give off different colors in fireworks or neon signs.
Yeah, definitely.
Well, if you pass that light through a prism, you don't see a continuous rainbow like sunlight. You see a set of distinct, sharp lines.
Like a barcode for each element, very specific.
Exactly. This discreteness was a huge clue that something discrete, something quantized, was happening inside the atom. Now, Rutherford's model of the atom, proposed a few years earlier, pictured a tiny, dense, positively charged nucleus with electrons orbiting it, kind of like a mini solar system.
Planetary model.
Right. But as we kind of touched on earlier, classical physics predicted that an orbiting electron, because it's accelerating, should continuously radiate energy. And as it loses energy, it should quickly spiral into the nucleus, making atoms unstable.
Which obviously doesn't happen. Atoms are stable.
Exactly. Atoms are stable, and they emit light only at those specific discrete frequencies shown in their spectra. So classical physics predicted atoms should collapse and emit continuous light, but reality showed stable atoms emitting only very specific colors.
A major contradiction. So enter Niels Bohr.
Enter Niels Bohr, a young Danish physicist working with Rutherford. He made his breakthrough in 1913. Bohr initially came to atomic structure from thinking about problems with electrons in metals, which hinted at some kind of non-classical stability, possibly involving quantum effects. He applied this intuition to Rutherford's model. Then, a colleague showed him the data on the remarkably simple, regular pattern of lines in the hydrogen spectrum, the Balmer series.
And he saw the connection, how to link his quantum ideas to these specific spectral lines.
Yes. Bohr realized he could explain both the atom's stability and the discrete spectra by proposing a really radical departure from classical physics. He put forward these postulates that seemed very ad hoc at the time. Electrons can only exist in certain specific stable orbits or stationary states around the nucleus.
Okay, only specific orbits allowed.
Right. And while they're in these orbits, they don't radiate energy, completely defying classical electrodynamics. Light is only emitted or absorbed when an electron jumps or makes a transition from one stable orbit to another.
A quantum leap.
Literally. And the energy difference between the orbits dictated the frequency of the emitted light, using Planck's relation again, EF.
So EEHF. The energy difference determines the light color.
Precisely. The frequency of the emitted light was given by AE equals HF, where AE is the energy difference between the initial and final orbits. Now, to make his model fit the specific lines of the hydrogen spectrum, Bohr found the energies of these allowed orbits had to be quantized according to a simple formula. He later justified this by proposing that the angular momentum of the electron in these allowed orbits also had to be quantized, but in units of Planck's constant h.
So his model was a strange hybrid, wasn't it? Using some classical concepts like orbits, but imposing entirely non-classical rules, no radiation in orbits, sudden jumps, quantized energy levels, quantized angular momentum, and crucially, the frequency of the emitted light wasn't the same as the electron's orbital frequency, another big break from classical intuition. How did this get accepted? It sounds pretty weird.
It was weird, and initially it was met with considerable skepticism because of its ad hoc nature and its blatant disregard for classical laws inside the atom. But what won people over were, well, two things mainly. The model's successes in exploiting existing experimental data, particularly atomic spectra, and crucially, its ability to make incredibly accurate predictions that were then confirmed by new experiments.
Ah, predictive power, that's key.
Absolutely. One particularly convincing result was a calculation Bohr did predicting a tiny shift of the spectral lines due to the nucleus's motion, like the nucleus isn't perfectly stationary.
Yeah.
His prediction matched experimental results to an astonishing 3 parts in 100,000. That level of agreement was just really hard to ignore.
Okay, yeah. The predictive power of these strange new rules started to outweigh the discomfort with how non-classical they were. And Einstein got involved again here, too.
Yes. Einstein returned to the interaction of light and matter with papers in 1916 and 1917. He formalized the processes of absorption, spontaneous emission, and stimulated emission of radiation based on Bohr's picture of discrete atomic energy levels. This work was fundamental. It linked Planck's law, Bohr's atom, and the concept of photons, and it laid the theoretical groundwork that would much later be essential for understanding how lasers work.
Stimulated emission. Yeah, the L
That-
in laser.
exactly. He also further solidified the idea of the photon as a particle and really stressed the probabilistic nature of these transitions. You couldn't predict when a specific atom would emit a photon, only the probability of it happening in a given time.
Probability again. First hinted at maybe with Planck, then Einstein with photons, and now with atomic transitions. Classical physics was all about certainty, wasn't it? Quantum physics seems to be injecting chance at a really fundamental level.
That's a major theme that continues right through the development of the theory and, frankly, continues to challenge our intuition even today.
Okay, so Bohr gave us the first successful quantized atom, explaining stability and spectra. What came next in the timeline? Roughly the late 1910s and early 1920s. What was that period like?
That period is often called the old quantum theory. Physicists basically took Bohr's model and tried to refine it, generalize it, make it work for more complex atoms and systems. They started incorporating relativistic effects. Sommerfeld was key. They're added more quantum numbers needed to describe the electron states beyond just the energy level and generalize the rules for quantizing angular momentum to more complex types of motion.
So building on Bohr's foundation, trying to flesh it out using his framework.
Yes, and they often use techniques and analogies drawn from 19th century classical physics, for example, drawing parallels to celestial mechanics, the math used for planetary orbits, to try and describe the allowed electron orbits. Experimental spectroscopy remained absolutely vital during this time.
Still driving the theory.
Completely. Spectroscopists were providing increasingly detailed data on the positions and intensities of spectral lines, and crucially, how these lines split when atoms were placed in electric fields, that's the Stark effect, or magnetic fields, the Zeeman effect. Theorists like P. Epstein worked incredibly hard to explain these intricate patterns using the developing quantum rules.
It sounds like a period of really intense, intricate work, almost like puzzle solving, trying to make the quantum rules fit the ever more precise experimental data.
That's a good way to put it. Our sources describe the young generation of physicists coming up during this time, including future giants like Kramers, Pauli, Heisenberg, and Jordan, often mentored by Bohr, Sommerfeld, born as practicing a kind of tightrope kind of theorizing. They were constantly balancing the experimental evidence with the still somewhat ambiguous and ad hoc quantum rules. Classical physics remained their touchstone, guide for identifying the possible motions before applying the quantum conditions.
And Bohr's correspondence principle was important during this time, wasn't it? What was that about?
Very much so. This principle, developed by Bohr, was a crucial guide. It essentially stated that for large systems or high quantum numbers, situations approaching the classical limit, like very large electron orbits, the predictions of the quantum theory must smoothly transition into the predictions of classical physics.
Ah, okay.
For example, for very large electron orbits, the frequency of light emitted during a jump between adjacent orbits should approach the frequency at which the electron is actually revolving in its orbit, just like classical electrodynamics would predict. This principle helped guide theorists in developing the rules and selecting which classical variables needed to be quantized.
So it helped build the quantum theory by ensuring it didn't completely contradict classical physics in the regime where classical physics was known to work, a kind of reality check.
Exactly. It provided a crucial link and a way to test the consistency of the emerging theory. And throughout this period, the experimental evidence for the quantum nature of reality just kept mounting. Experiments like Planck and Hertz's back in 1914, which directly measured the discrete amounts of energy, the resonance potentials that atoms could absorb before emitting light, provided really powerful support for the idea of quantized energy levels.
More direct proof of discrete levels.
Yes, and further precise measurements of X-ray spectra, confirming the energy levels in heavier elements, continued confirmation of the photoelectric effect by Millikan, studies of photochemical reactions, all these different kinds of experiments yielded consistent values for Planck's constant H, further solidifying its fundamental importance.
So Mach wasn't just some parameter popping up in one or two puzzles anymore. It was showing up consistently across really diverse physical phenomena, a truly fundamental constant.
Yeah, providing an overwhelming case for the existence of the quantum of action H, as one source puts it. The value of H was being determined repeatedly, around 6.54 by 1027 erg seconds in those older units, from completely different experiments.
Yeah.
But despite all these successes, the fundamental paradoxes and the general weirdness remained.
Like what? What were the lingering problems?
Well, the big ones. Why exactly don't electrons in stationary states radiate energy, as classical theory absolutely demands they should? How can the frequency of emitted light be totally different from the electron's orbital frequency? The quantum, as one source notes, still felt like an intruder that was kind of undermining the old, comfortable classical structure without providing a fully coherent replacement.
Still felt a bit like patches on an old system.
Sort of. And the wave versus particle dilemma, which had been reignited by Einstein for light, was about to become even more acute. The historical debate between Huygens wave theory and Newton's particle theory for light, which everyone thought had been settled in favor of waves by interference experiments, was suddenly back, stronger than ever. And it was starting to suggest that maybe even matter might have this weird dual nature. It was, as one source describes it, a serious dilemma.
So the old quantum theory was successful in explaining a lot, but it felt incomplete, right? Like a set of rules that worked but weren't fully understood from a fundamental perspective. This sets the stage for the mid-1920s and the development of modern quantum mechanics, aiming for that deeper, unified framework.
Precisely. The need for a consistent, fundamental theory to replace the sort of ad hoc rules of the old quantum theory was becoming really clear. This is where these new, more formal mathematical frameworks emerged. Werner Heisenberg, working with Max Born and Pascual Jordan, developed matrix mechanics in 1925. It was a powerful but quite abstract approach that focused only on observable quantities like the energy transitions between states.
Matrices doesn't sound very intuitive for visualizing particles or waves, does it?
No, it was very abstract, based on these mathematical entities, matrices, that don't commute the order you multiply them matters. And then just a year later, in 1926, Erwin Schrödinger introduced a completely different-looking but, as it turned out, equivalent formulation. Waves mechanics, based on a partial differential equation, the now famous Schrödinger equation.
Okay, let's try to get an intuition for this equation because it's so central to modern quantum mechanics. How did Schrödinger actually come up with it? Was it derived from first principles?
Not really a strict derivation, no. Our sources describe it more as a highly educated guess, maybe a brilliant construction based on physical intuition and the recent ideas floating around, especially to prose these. The starting point, as one source explains it, was the classical expression for the total energy of a particle. Energy, E, equals its kinetic energy, which is momentum squared over twice the mass, p20 areas, plus its potential energy, Vx, which depends on its position. So classically, E equals p20 meters plus Vx.
Standard classical physics so far. Nothing weird yet.
Right. But then you bring in Louis de Broglie's revolutionary idea from 1924 that all particles, not just photons, have waves associated with them. And crucially, that their energy E and momentum P are related to the frequency omega and wave number K of these waves by the same quantum relationships Planck and Einstein found for photons. E equals h bar omega and P equals h bar K. Remember, h bar is just Planck's constant h divided by 2p.
Okay, the quantum dictionary connecting particle properties, would be P, to wave properties, omega K.
Exactly. Schrödinger essentially asked himself, if particles have waves associated with them, there must be some kind of wave equation that governs how these matter waves behave over time and space. He looked for a mathematical equation where applying certain derivatives to a wave function, which he called psi k, would effectively pull out factors of omega and k in a way that mirrored the structure of that classical energy equation, E equals P would be 2 meter plus V, but using these quantum E, omega, and pk relations.
So he needed an equation where, like, taking a time derivative gives you something related to energy, and taking spatial derivatives gives you something related to momentum squared.
That's the core intuition behind the time-dependent Schrödinger equation. I to bar EOP power plus VOP AP. It looks complicated, but the term with the time derivative relates to energy E, and the term with the second spatial derivative relates to momentum squared. POP relates to the momentum squared, POP. This equation describes how the wave function evolves over time.
Okay, and what about those stable states, like electron orbits?
Right. If you're looking for states with a definite energy E, like those stationary states in Bohr's atom, which are stable over time, you look for solutions where the time dependence is simple, just an oscillation with frequency omega a bar. This leads to the time-independent Schrödinger equation, E h bar 2 meters plus V at x. Solving this equation for a given potential energy Vx tells you which wave functions are allowed, and critically, it only works for specific discrete energy values E, which naturally explains the quantized energy levels that Bohr had to postulate.
Ah, so the quantization comes out naturally from solving the wave equation, not just put in by hand. That's a big step. And the wave functions itself, what is this mathematical thing?
Well, that was the next big question. Mathematically, it's complex. Literally, it involves the imaginary number. You see it in the time-dependent equation. Unlike classical waves, where we often just care about the real part, the entire complex function is important in quantum mechanics, although the quantities you actually measure always turn out to be real numbers. Initially, Schrödinger himself speculated that maybe Uraclee represented some kind of smeared-out charge density for the electron, like the electron was literally spread out as a wave.
That would kind of make intuitive sense if it's a matter wave, wouldn't it?
It would seem to, yeah. But that interpretation turned out to be wrong, or at least incomplete. The correct and really revolutionary interpretation came from Max Born, also in 1926. Born proposed that the wave function itself isn't directly physical, but the square of its absolute value at a given point represents the probability density of finding the particle at that position if you were to look for it. This is the famous Born rule.
The Born rule. Okay, pause there. So the wave function isn't the particle itself spread out. It's a description of the probability of finding the particle somewhere if you were to make a measurement.
Exactly. And here's where it gets really strange and fundamentally challenges our deepest intuitions about reality. As one of our sources explicitly states, this probability is not like the probability in a coin toss, where it's just due to our ignorance of the exact starting conditions. In quantum mechanics, this probability is considered truly random.
Truly random. Meaning?
Meaning the particle doesn't have a definite position or momentum before you measure it. The wave function describes its potential, its probabilistic existence across multiple possibilities simultaneously. That's superposition. It's only when you make a measurement, when the system interacts with a measuring device, that the wave function seems to collapse into a single definite outcome, and you find the particle at one specific place.
Wow. Okay. That idea that randomness is fundamental, not just a reflection of missing information, that must have been incredibly unsettling, especially to people like Einstein.
Deeply unsettling. It led to decades of debate and the search for hidden variables, hypothetical underlying properties that, if we could only know them, would restore determinism and tell us exactly where the particle really was all along. But experiments, especially those spurred by John Bell's theorem in the 1960s, have consistently ruled out the most plausible types of local hidden variable theories. The evidence strongly supports the inherent probabilistic nature that quantum mechanics describes.
So modern quantum mechanics, in its most fundamental description, is truly probabilistic. That's a massive departure from the deterministic, predictable clockwork universe of classical physics. And then Paul Dirac came along shortly after Schrödinger and Heisenberg.
Yes. Also in 1926, Paul Dirac provided the crucial mathematical proof showing that Heisenberg's matrix mechanics and Schrödinger's wave mechanics, despite looking completely different on the surface, were actually mathematically equivalent formulations of the same underlying theory. They were just different perspectives on the same quantum reality. This really solidified the foundation of modern quantum mechanics, providing a consistent and powerful theoretical framework.
Okay, so with this new unified framework established by the mid-1920s, let's revisit those core, really bizarre concepts that make quantum mechanics so fascinating and counterintuitive. First up, wave-particle duality, but now applied to all particles thanks to de Broglie.
Right. De Broglie's 1924 hypothesis was just revolutionary. If light waves can sometimes act like particles, photons, then maybe particles like electrons, protons, or even whole atoms could sometimes act like waves, following the same relationships, E bar omega and P each bar K. And this wasn't just speculation, it was quickly confirmed experimentally through electron diffraction experiments. Scientists like Davison and Germer and independently G.P. Thomson showed that beams of electrons fired through crystals produced interference patterns, exactly like X-rays, which are waves, do.
So electrons, which we normally think of as tiny little balls, can actually diffract and interfere like waves.
Exactly. The behavior depends entirely on the experiment you set up. In the photoelectric effect, light acts like particles, photons. Send light through a double slit, it acts like waves, creating interference. Electrons used in an electron microscope act like waves. Their very short wavelengths allow for much higher resolution than light microscopes. But when electrons hit the screen in an old CRT television, they make individual spots, acting like particles.
So they're neither purely waves nor purely particles.
There's something else entirely, described by this wave function, that exhibits aspects of both, depending on how you interact with them or measure them. As one source dryly notes, few people understand it in a truly intuitive classical sense. It's just how the quantum world works.
Okay, wave-particle duality for everything. Got it, sort of. What's the next big, strange concept that solidified in this era?
The Heisenberg uncertainty principle, formulated by Werner Heisenberg in 1927. This puts a hard mathematical limit on how precisely you can know certain pairs of properties for a quantum particle simultaneously. The most famous pair is position, Let's say the uncertainty in position is x, and momentum, uncertainty. The principle states that the product of these uncertainties can never be smaller than a certain fundamental value related to Planck's constant, h u star 2.
So the more precisely I know where a particle is, small x, the less precisely I can possibly know its momentum, large M, and vice versa. You can't know both perfectly at the same time.
Exactly. And it's really crucial to understand why. As our source explains, it's not just the limitation of our measuring instruments or the common idea that measuring position inevitably disturbs momentum, though that measurement disturbance effect does happen. The uncertain principle is actually a direct mathematical consequence of the wave nature of matter itself and how waves are described using Fourier analysis.
Fourier analysis, how does that connect?
Think about building a wave shape.
Yeah.
If you want a wave function, tex x, that's sharply peaked, describing a particle localized in a very narrow region of space, meaning Trox is very small, its position precisely, you mathematically need to combine a very wide range of simple sine waves with different wavelengths or wave numbers, k, to build up that sharp peak.
Okay, like building a sharp sound pulse requires many frequencies.
Exactly the same idea.
Yeah.
And since momentum p is directly proportional to wave number, p equals h bar k, meeting a wide spread in wave numbers k to get a small tox means you automatically have a wide spread in possible momentum values. Test is large. Conversely, if you want a wave function made up of a very narrow range of wave numbers, meaning you know the momentum very precisely, that wave function tex x will necessarily be spread out over a large region of space. Xx will be large.
So it's a fundamental trade-off inherent in describing something with wave-like properties. The math forces it.
Precisely. The uncertainty principle is baked into the mathematical structure of quantum mechanics via the wave function. No amount of experimental cleverness can ever beat this fundamental limit. It really means that at the quantum level, properties like position and momentum don't even have single, definite, simultaneously precise values in the way we intuitively understand them from classical physics. The fuzziness is inherent.
Duality, probability, uncertainty. It's painting a picture of a universe that's fundamentally fuzzy and probabilistic at its core, at least until we force an answer by measuring it. What's another really counterintuitive prediction that modern quantum mechanics gives us?
Quantum tunneling. This phenomenon started being explored theoretically around 1927, and it's perhaps one of the most mind-bending concepts when you compare it to classical physics. Classically, imagine a ball rolling towards a hill. If the ball doesn't have enough energy to get over the top of the hill, its kinetic energy is less than the potential energy needed to reach the peak. It simply rolls partway up, stops, and rolls back down. Its probability of being found on the other side of the hill is absolutely zero.
Makes perfect sense classically. You need enough energy to overcome the barrier.
Right. Energy conservation dictates it. But in quantum mechanics, the story is completely different. When a particle's wave function encounters such an energy barrier, a region where the potential energy V is higher than the particle's total energy E, the wave function doesn't just hit a wall and stop. The Schrödinger equation tells us that the wave function actually penetrates into the barrier region. It doesn't propagate like a normal wave inside, but it becomes what's called an evanescent wave. It decays exponentially.
It decays, but it doesn't instantly vanish.
No, it drops off rapidly, but it doesn't necessarily reach zero unless the barrier is infinitely wide or infinitely high. And here's the absolute key. If the barrier has a finite width, the exponentially decaying wave function can still have a small but non-zero value on the other side of the barrier when it emerges.
And according to Born's rule, if the wave function is non-zero,
right, it means there is a non-zero probability of finding the particle on the other side of the barrier, even though it classically had insufficient energy to ever get there. It's as if the particle has tunneled right through the classically forbidden region.
Okay, wait, it just appears on the other side?
Probabilistically, yes. Our source uses a neat analogy. Imagine a wave traveling on a string that encounters a segment loaded with springs. If the wave's frequency is below the natural frequency of the springs, the wave becomes evanescent. It decays exponentially within that springy segment. But if the segment is finite, a wave will still emerge on the other side, just with a smaller amplitude. Particle tunneling is the analogous but much more bizarre quantum effect for matter waves.
That is truly wild. A particle can literally pass through a wall even if it doesn't have enough energy to go over it. Does this actually happen in the real world, or is it just some theoretical quirk?
Well, it absolutely happens, and it's essential for understanding many natural phenomena and crucial for modern technologies. It's how alpha decay works in some radioactive nuclei. An alpha particle literally tunnels out of the strong nuclear force barrier holding it inside the nucleus. It's fundamental to how electrons move in semiconductors, forming the basis of devices like tunnel diodes. And it's exploited directly in modern flash memory.
Like in USB drives and SSDs.
Exactly. Data is stored by forcing electrons to tunnel through a very thin insulating layer onto a floating gate. And maybe the most direct visualization is the scanning tunneling microscope, STM, invented in the 1980s. It uses the quantum tunneling of electrons between an incredibly sharp metal tip and a conducting surface to create images with atomic scale resolution. The tunneling current is exquisitely sensitive to the distance, allowing you to map surfaces atom by atom. It's a technology built entirely on harnessing this bizarre quantum effect.
Wow. So, okay, from Planck's reluctant constant and Einstein's radical quanta through the ad hoc rules of the old quantum theory, and then the formal probabilistic framework of modern quantum mechanics with its inherent uncertainty and bizarre tunneling predictions, we've arrived at a point where these incredibly strange ideas are starting to be not just understood theoretically, but actually harnessed. This takes us into the era of experimental milestones and the beginnings of the quantum technology boom.
Yes, exactly. The story progresses naturally from figuring out the fundamental rules of the quantum world to applying those rules to build new tools, make new kinds of measurements, and eventually create entirely new technologies. An early example on the timeline is the development of the first atomic clock in 1949.
Atomic clocks, how do they use quantum mechanics?
They exploit the incredibly precise and stable frequencies associated with specific electron transitions within atoms, those discrete energy levels predicted by quantum mechanics. By locking an electronic oscillator to the frequency of one of these atomic transitions, like in cesium atoms, you can create a time standard far more accurate than any previous mechanical or electrical clock. It's precision measurement enabled directly by quantum energy levels.
So precision measurement was one of the first big practical impacts.
Definitely. And the timeline also highlights other important steps in the mid-20th century, like superconducting devices. The Josephson junction, 1963, and squeUDs, or superconducting quantum interference devices, 1964, were really significant. These devices operate at very low temperatures where materials become superconducting, and they exhibit macroscopic quantum effects.
Macroscopic, meaning quantum effects you can see on a larger scale.
In a sense, yes. Squids, for example, use the quantum interference of electron pairs, Cooper pairs, flowing in superconducting loops. This interference makes them incredibly sensitive to tiny changes in magnetic fields. They were foundational in showing that quantum mechanics isn't strictly limited to single atoms or particles. Its strange effects like superposition and interference can manifest in collective ways in specially prepared systems, allowing for new kinds of sensors.
And the experiments didn't just stop at applying the concepts. Some were designed to test the very philosophical underpinnings of this weird new reality, right? Like the debates Einstein had.
Exactly. That leads us to John Bell's work in 1964. He developed a theoretical framework known as Bell's inequalities that provided a way to experimentally test the predictions of quantum mechanics, particularly its non-local features like entanglement against a whole class of alternative theories based on classical intuition. These classical ideas usually involve local realism, the assumptions that physical properties exist independently of whether we measure them, realism, and that influences cannot travel faster than light, locality.
So Bell figured out a way to make philosophy testable in the labs.
Essentially, yes. His inequalities set mathematical bounds on the correlations you could expect to see between measurements on separated particles if local realism held true. Quantum mechanics, with entanglement, predicted correlations that could violate these bounds. And experiments, particularly Alain Aspect's groundbreaking work in 1982 and many refined versions since, have consistently shown violations of Bell's inequalities, providing incredibly strong evidence against local realism and supporting the counterintuitive predictions of quantum mechanics, especially entanglement.
Confirming that the quantum world really is as strange as the theory suggests, and that the apparent randomness isn't just about missing local information. Entanglement is real.
Right. And other theoretical results also shape the landscape. For instance, the no-cloning theorem, proved around 1970, showed that it's fundamentally impossible to create a perfect, independent copy there of an arbitrary unknown quantum state. You can't just quantum Xerox something. This highlighted a fundamental difference between quantum information and classical information, which you can copy perfectly, and had significant implications for the nascent field of quantum information processing.
Okay. Which brings us more towards the present day, the late 20th century onwards, this era of actively trying to leverage these fundamental quantum phenomena, especially superposition and entanglement, to build entirely new classes of technology. This is the quantum technology boom we hear about.
Yes, it's really about moving from simply explaining the natural world with quantum mechanics to actively engineering systems that exploit quantum effects to perform useful tasks, tasks that classical technologies might struggle with or simply cannot do at all.
Like quantum communication, making communication more secure.
That's a prime example. Quantum key distribution, or QKD, first proposed theoretically in 1984 with protocols like BB84, allows two parties, traditionally called Alice and Bob, to generate a shared secret cryptographic key using quantum principles. The security doesn't rely on mathematical difficulty like current encryption, but on the fundamental laws of quantum mechanics.
How does that work, basically?
The core idea is that they exchange quantum states, like photons with specific polarizations. If an eavesdropper, Eve, tries to intercept and measure these quantum signals to learn the key, her measurement will inevitably disturb the quantum states in a detectable way. Because of things like the uncertainty principle and the no-cloning theorem, she can't measure them without leaving traces. Alice and Bob can then test a portion of their exchange states for these errors. If they find too many errors, they know someone was listening, and they discard the key and try again.
So security guaranteed by the laws of physics itself. Pretty cool.
It is pretty cool. And you can see on the timeline the rapid progress in this area. From the first experimental implementation in 1989 to demonstrations of distributing entangled particles over significant distances in 1997, proposals for quantum repeaters needed to extend the range beyond fiber optic losses, and experimental links spanning hundreds and eventually thousands of kilometers by the 2000s. More recently, we're seeing real-world deployments in niche applications and increasing complexity in developing quantum networks.
And the other big area, the technology field that probably gets the most headlines, quantum computing.
Ah, yes, the grand challenge. The goal here is to build computers that use quantum bits, or qubits, instead of classical bits. Unlike a classical bit, which can only be 0 or 1, a qubit can exist in a superposition of both 0 and 1 simultaneously. And multiple qubits can be linked together through entanglement.
And this allows them to do calculations differently.
Vastly differently. These properties allow quantum computers to explore a huge number of possibilities in parallel and exploit quantum interference to find solutions to certain types of problems much faster than any classical computer ever could, even supercomputers.
What kinds of problems? Are we talking faster web browsing?
Not really for everyday tasks like that. The potential power lies in specific areas. The theoretical foundation came from algorithms like David Deutsch's in 1985, which first showed a quantum computer could solve a contrived problem faster than classically possible. Then came the big one, Peter Shor's algorithm in 1994 for efficiently factoring large numbers.
Factoring large numbers, why is that important?
Because the security of most modern encryption, like RSA used for secure websites and banking, relies on the fact that factoring large numbers is incredibly difficult for classical computers. Shor's algorithm showed that a large-scale quantum computer could, in principle, break this type of encryption easily, which has massive implications for cybersecurity. Lovegrover's algorithm in 1996 showed a quadratic speedup for searching unstructured databases, which is also significant.
Okay, so potentially game-changing algorithms exist, but building the actual hardware is the hard part.
Incredibly challenging. You need to create qubits that are well isolated from environmental noise, which destroys quantum states, but also controllable and able to interact with each other to perform logical operations. The timeline shows the sheer variety of physical systems being explored globally to try and achieve this. Superconducting circuits cooled to near absolute zero, individual ions trapped by electromagnetic fields and manipulated with lasers, photons traveling through optical circuits, even more exotic ideas like topological qubits. We see milestones like demonstrating entanglement between qubits 2002 and building basic quantum logic gates like the CNOT gate 2003 as foundational steps.
And we're seeing more and more experimental progress announced regularly now, aren't we?
We certainly are. From researchers providing access to early quantum processors via the cloud starting around 2013, to demonstrations of 2-qubit logic gates in silicon, a promising platform, due to the existing semiconductor industry. In 2015, IBM making its quantum computers accessible online for experimentation in 2016. And then you have the highly publicized demonstrations claiming quantum advantage or quantum supremacy.
Right, like Google's Sycamore processor in 2019, what did that actually achieve?
Google claimed their Sycamore processor performed a specific, carefully chosen computational task, basically sampling the output of a random quantum circuit exponentially faster than even the most powerful classical supercomputer could simulate it. There was debate about the claim and whether classical algorithms could be improved, but it was a landmark demonstration of quantum hardware reaching a scale and complexity where it could, at least for one specific task, outperform classical machines. Similar claims followed from teams in China using different platforms like photonic systems, boson sampling, and superconducting qubits. Metrics like quantum volume were introduced around 2017 to try and provide a more holistic benchmark of a quantum computer's overall performance beyond just qubit count.
So it's a really rapidly advancing field, moving from just theory to actual experimental realization, even if large-scale fault-tolerant machines are still a way off. But quantum isn't just about computing and communication, right? It's also revolutionizing measurement and sensing again.
Absolutely. That's the field of quantum metrology and sensing, building on those early ideas like the atomic clock, but pushing things much further. We saw the atomic clock earlier, but the timeline lists other compelling examples. Quantum gravimeters were developed around 1998. They use the wave nature of atoms manipulated in superposition states, atom interferometry, to measure tiny variations in the local gravitational field with extreme precision. This could be useful for geology, resource exploration, or navigation where GPS isn't available.
Using atom waves to sense gravity. Cool.
And quantum effects are also being cleverly integrated into existing cutting-edge classical instruments to push their sensitivity beyond classical limits. A fantastic example is the use of squeezed light, a special non-classical quantum state of light where the uncertainty in one property, like amplitude, is reduced below the standard quantum limit, at the expense of increased uncertainty in another property, like phase. Injecting squeezed light into the interferometers of the LIGO and Virgo gravitational wave detectors in 2018 significantly reduced the quantum noise that limited their sensitivity, allowing them to detect weaker or more distant gravitational wave signals from merging black holes and neutron stars.
So using quantum weirdness, like squeeze uncertainty, to make something like a gravitational wave detector even better at spotting ripples in space-time, that's amazing.
It really is. And we're seeing ongoing demonstrations of quantum advantage in areas like microscopy, reported 2021, potentially allowing for imaging biological samples with less damaging light exposure or achieving higher resolution, and the development of new sensor types like quantum gravity gradient sensors, 2022, which measure how gravity changes over short distances and could have applications for mapping underground structures to defense.
Looking back at this whole linear progression we've traced, it's just an incredible story, isn't it? It started with a small, seemingly technical problem with how hot objects glow, leading to a mathematical trick introduced reluctantly by Planck. Then Einstein radically interprets that trick as real energy packets in light itself. Bohr extends it to explain the stability and spectra of atoms using these strange, non-classical rules. It gets formalized into a fundamental probabilistic theory by Heisenberg, Schrödinger, Born, and Dirac. And its bizarre predictions like duality, uncertainty, and tunneling have been repeatedly confirmed by decades of experiments.
Yes, it's really a journey where physicists were repeatedly forced by experimental evidence to abandon comfortable classical assumptions, continuity, determinism, locality, objective reality, independent of measurement, and embrace a reality at the fundamental level that is profoundly counterintuitive, where energy, momentum, and other properties are quantized, where particles can act like waves and waves like particles, where outcomes are inherently probabilistic, and where particles can tunnel through barriers they shouldn't be able to cross. The history really shows the power of relentless experimentation in challenging our preconceived notions and forcing us to update our theories.
And why does knowing this history, understanding these core concepts, matter to us today, to you listening?
Because this isn't just abstract physics locked away in labs. The very strange rules of quantum mechanics, initially debated fiercely in rarefied academic circles, are actually the foundation for much of our modern technological world. Think about semiconductors. The transistors in every computer, smartphone, and electronic device rely on the quantum mechanical behavior of electrons and materials. Lasers, LEDs, MRI machines in hospitals all are fundamentally quantum technologies.
We're already living in a world built on the first quantum revolution.
Exactly. And now we are entering a second quantum revolution, where we are deliberately engineering systems to leverage the even more counterintuitive aspects of quantum mechanics, things like superposition and entanglement, to build entirely new capabilities. Capabilities in computing, in secure communication, in ultra-precise sensing that were previously unimaginable using only classical physics. The aha moment is realizing that the weirdness isn't just a philosophical curiosity, it's functional. It's the resource that enables these powerful macroscopic technologies that are already beginning to impact your life and will undoubtedly continue to shape the future in profound ways.
It's truly remarkable how, just over a century ago, a subtle problem with the color of light from heated objects ended up triggering this entire revolution in physics and technology.
It really underscores that sometimes the biggest breakthroughs come from investigating the most seemingly obscure corners, driven by fundamental curiosity about how the universe works.
We've seen how embracing probability, uncertainty, and the truly bizarre nature of quantum states has been absolutely essential to developing both the theory itself and the technologies it now enables. But despite all this incredible progress, one of the sources touched on this, exactly how a measurement seemingly forces a quantum system to collapse out of its fuzzy, probabilistic state of potential, the wave function, into a single, definite outcome remains one of the biggest unresolved questions in fundamental physics. It's often called the measurement problem. What is the fact that this fundamental aspect of interaction, observation, and reality itself is still shrouded in mystery? Tell us about the nature of the universe, and maybe even our own place within it.
That's a deep question, and one that continues to fuel debate, research, and future exploration. The story definitely isn't over yet.
Absolutely. Well, this deep dive was made possible by the fascinating sources you shared with us. Thank you for providing them and sparking this incredible journey through the history and concepts of the quantum world. We really hope it's given you a clearer picture of this revolutionary field and why it continues to be so important and, frankly, so mind-bending. Keep that curiosity buzzing.